In the first video of this section, we talked about the first fundamental theorem of calculus, which showed how the definite integral and the antiderivative correspond. But there's also another way in which derivatives and integrals correspond, and that's the second fundamental theorem of calculus's role here. So let's look at this first warm-up. Here we have a function y, and this function is written in terms of a definite integral from 5 to x. Now we call this an accumulation function because we're looking at, in some sense, the area or the region under a curve from 5 to some place down the road. So let's look at evaluating this definite integral and seeing what y is in terms of x. So y equals the integral from 5 to x of 3t squared dt. Finding an antiderivative of 3t squared means that we're going to raise the power on t and divide by that new power. And we'll evaluate this from 5 to x. But this is equal to t cubed evaluated from 5 to x. So we have x cubed minus 5 cubed, or x cubed minus 125. Now, that means y equals x cubed minus 125. In the second warm-up, we want to find the derivative of that. That's not too difficult. dy dx equals 3x squared. The point of this second warm-up is not because it was difficult, but to show you how what we began with, the integrand, and our derivative now match, except for the t squared dt, we now have x squared. We call, in the original problem, t, we call that a dummy variable because it really doesn't matter what t was. If t had been instead h, then h would have gotten replaced eventually by x and 5. H would disappear. Or we could have called it theta. Regardless, it doesn't matter. T is just standing in the place of whatever comes next after we evaluate our definite integral. The point being here is, if we look at this integrand and then we look at what we arrive at after taking the derivative, it's almost as though the definite integral is undone by the derivative. So, if you notice, we have the derivative with respect to x, and we have the integral from a to x. And t is again just a dummy variable, standing in the place of whatever happens next. So, the derivative with respect to x of the integral from a to x is going to yield for us just f of x. So you'll notice the integrand and the answer. So the derivative acts on this definite integral, and the result is the integrand, and we replace the independent variable with the variable we are differentiating with respect to. So let's look at an example of this. Here we have a function, capital F, and it's a definite integral evaluated from 1 to x. Now it's possible that we could go ahead and do this like warm-up 1 and evaluate the definite integral. It's possible, but we don't have the tools necessary in our calculus toolbox to actually find this definite integral. So therefore, what we must do is just to rely on that second fundamental theorem of calculus. So if I want to find the derivative with respect to x, then I'm looking at f prime of x equals the derivative with respect to x of the integral from 1 to x of t squared over t squared plus 1 dt. Now again, notice the variable we are differentiating with respect to matches that upper limit of integration. And because of that, the answer is simply take the integrand and replace t with our variable that we are differentiating with respect to. Now in this situation, let's take a quick look at what we're facing. We have the goal set before us is to find f prime of x, but what we're going to find is that whenever we differentiate with respect to x, we are facing a little bit of a different scenario. If you notice, we're differentiating with respect to x. However, the upper limit of integration is not x. The upper limit of integration is x squared. So what we want to do is we want to actually make a variable substitution, or just think of it as the chain rule. So let's remember the chain rule. Remember that if y is a function of x, we can find dy dx by taking dy du and multiplying by du dx. And we usually let u be that inside function. So in this case, let's let u equal x squared. So let's let u equal x squared. Then du dx is 2x. This also means that I'm going to go back and let this whole inside be y. So let's let y equal the integral from 0 to x squared of sine of theta squared d theta. But the nice thing here is this is the same thing as the integral from 0 to u of sine of theta squared d theta. Now, as we look at what we've arrived at, we have f prime of x equals the derivative with respect to x, I'm just rewriting here, the integral from 0 to x squared sine of theta squared d theta. But that is the same thing as the derivative of y with respect to x, which we know is the same thing by the chain rule as dy du times du dx. Well, what is dy du? If I look back here, dy du is an application of the second fundamental theorem of calculus. So we have dy du is the derivative with respect to u of y. But what's y? Y is the integral from 0 to u of sine of theta squared d theta. And du dx, we've already established, as 2x. So from the second fundamental theorem of calculus, we now have the independent variable and the variable we are differentiating with respect to match. The upper limit of integration and the variable we are differentiating with respect to match. So therefore, it's just going to be sine of, not theta squared. Theta was just a dummy variable. We were replacing that dummy variable with the variable we are differentiating with respect to. So sine of u squared. And that is going to be multiplied by 2x afterward. So this is going to be 2x, and then sine, and we don't have u in the original problem. We have u is x squared. So we're going to replace the u with the x squared. So u squared would be x squared squared. So x to the fourth. And thus ends the problem.